Hi, so can you hear me okay? If you ever cannot hear me, fine, wave or something, because I don't speak very loudly normally, so the microphone is good. But if we lose the microphone, then just let me know. And just to get a feeling of the room, how many people have a Spark in production here? Just to make sure. Okay, so a bunch of guys. So yeah, right. So you don't need to be convinced about anything. So part of the talk will be completely unnecessary for you. Right, how many people here have looked at Scala? Just out of curiosity. Okay. Right. Okay, so I'm going to tell you about my experience looking at Scala and Spark. So I'm the director of Data Science Retreat, and we've been teaching machine learning, data engineering for like 3 years, mostly with Python and R. And recently, in the last year or so, we started using Scala to teach and to do delivery projects and so on. So I have done the same task twice, once in Python and once in scala-Spark, and then I can tell you what my feelings were when I did the same thing twice. So to start with, kind of the obvious introduction. So Python and Scala languages, sort of very large, all-encompassing machine learning tools, libraries. Actually, Spark is not only machine learning, it's a whole bunch of other things. And the main thing that differentiates them is that in the left side of the ring, you have one machine only, so you have to worry about the memory of one machine, the CPU of one machine. And in this part of the world, the whole game is to be distributed. So that's basically the main thing that this discussion is going to be about, right? So for me, it's important to answer a question with this talk. So the question will be like, why should I bother to go to this side, right? Right, so why this talk? Well, how do you go from a single machine to multiple machines? And apparently the obvious answer now is Spark machine learning. And the lingering question here could be like, am I missing out if I'm staging in the Python world, right? So I don't know if I'm going to be able to answer that question. It's kind of a very personal thing, but I'm going to try to give you my view of the world. Right, so you may be thinking, well, yeah, Spark, there is PySpark, so why do I bother? So I just stay with PySpark, right? So one thing that I'm going to cover here is the dangers of using PySpark. So there are some consequences of not being on the native platform, sort of. It's not horrible, but it's not ideal either. So, right, so data science retreat. So if you don't know about this, it works as, it's a retreat. So it's for people who know what they are doing, but they want to be much better. And then they fly from all parts of the world, like literally, like Brazil, Korea, Vietnam, yeah, all kind of weird places. They come to Berlin for 3 months, and we hit them very hard with basically all the state-of-the-art things that we can imagine. Mostly streaming, machine learning, deep nets are becoming a big thing. All the things that you think, oh, I could learn this by myself, but it would take such a long time. So then you get some badass to just show you how he does things, and then you get the best practices and so on. I think that's the way people are attracted to this, right? So the mentors are pretty interesting people in general. We accept very few people, but that's just normal. I mean, many applications are not that interesting. Some of them are interesting, but they're missing one little bit, which could be they don't know machine learning. So they could be kick-ass BI guys who know SQL like better than you, but they don't know machine learning, and then you send them back and they study and they come back to you. Right, so we really want them to be able to communicate well with stakeholders and people who don't understand machine learning. That's very important, because I've seen many projects fail to get support just because the data scientists don't know how to explain to the rest of the company what they're doing. And then who is this guy who is walking around costing us a lot of money and nobody understands what he's doing? So we want to avoid that. So there are technical communication sessions where you just improve your communication skills, basically. People, when they come, they have about 5 years of experience on average. And we work with a bunch of companies who want to hire talent, and apparently these companies are very happy because they keep coming back. So I think that the problem that we are really solving, but I may be wrong, is that there is a valley of death. So there are a bunch of people who have certain amount of skill in data science that they can fit random forest, and they can tell you why a model is better than another. But there is like a huge area here where there is not much going on, and then you have the super good guys who could do 10x on your performance, and there is nothing in between. This is my experience. So I think this is what happens when you come to a super intensive retreat, that you kind of jump over the valley of death, or at least you try. Right, so examples of portfolio projects. Let me see if I can click on the screen, which I cannot, apparently. Well, it's a video of a participant who built a smile recognition system. So you could smile, and this bar will go green, and it could work with multiple faces on real-time video and so on. This was like 1.5 years ago. Now this is actually kind of common, but before it was not that common. So one of the attendants to hiring day raises his hand. He was there to hire, and then he says, like, "Why do you want a job? Like, just put this in production, make a company out of this, and don't get a job." And he actually did. So anyway, so right, he's actually working now on detecting fake smiles, which is kind of interesting. Right, in general, people are very happy. You can see smiley faces and so on. They keep in touch, and they tell everybody what they are doing. They are doing crazy stuff for pretty interesting companies. Right, so why is DSR talking about Scala and Spark here? So Lightbend is actually the company behind the Scala. They used to be called TypeSafe, but they changed their name, kind of like Google. And these guys got approached by IBM, who is running this big data university, to create training materials for data scientists who want to do things in Scala and in Spark, but they don't know how. They know the typical machine learning topics and so on, but they don't know the how, right? So then they approach us to create training materials for this big data university. They are videos. They are like 5 to 10 minutes, and they are to the point. So you want to run a credit boosted tree on Spark. This is how it works. This is how you compare it with other models. Right. So interestingly, in the market, apparently people who are doing Spark are really interested in doing it natively in Scala, and you will see why soon. There is plenty of Python for sure, but there is more Scala. I don't know what that means. So this is a totally subjective graph of programming languages in data science. I think R was super hot up to a certain point. It keeps growing, but it sort of got taken over. I don't even know. I don't have empirical data for this. This is just my gut feeling, basically by talking to data science badasses. So this could be not over, could be far ahead. I have no clue. I just draw in something that's my gut feeling. And what I think is happening is that Scala is about here. It's growing very fast, so the slope is higher than any of these two. And it's mostly about Spark. So most people go to Scala because they try the Spark, and it's such a nice match. So I would like this talk to give you a superpower. And for me, the superpower will be that if somebody approaches you to do a project on a Spark, and this is a company that is not using any Python, and they cannot do any Python, banks or big companies are like that, I want you to be able to say yes or maybe after this talk. This is a very big challenge, and you will see later on how we're going to get there, because I mean, with 40 minutes of talking, it's not going to happen. But I would like that to be the superpower that you get after this talk, to be able to say maybe to a project that is using Scala and Spark, even if assuming that you know Scikit-learn, Python really well, and you can do machine learning on your own, right? Right, so Scala. Scala has certain advantages. Apparently, one thing that people keep telling me is that they seem to refactor code very nicely because of the type system that is super sophisticated and complex, doing things for them. They don't rely on tests so much. Fine, I haven't experienced this. But the main thing to consider is that Scala and Spark are really, really close to each other. So if you learn one, you learn the other. And this is kind of a freebie. So if you really wanted to get very far with Spark, maybe one easy thing to do is to learn Scala, because the collections library is pretty much the same in Scala and Spark. So somebody thought, oh, what happens if we do the same thing that Scala is doing, but distributed? And that's Spark. So if you are really, really interested in getting deep into Spark, Scala is the way, basically. Because the same philosophy, the same mindset, it's there. You probably know that in Spark, there are plenty of other things. There is not only a machine learning library, and there is more than one now. There are SQL query engines, there are streaming processing things. This is changing very much now. And there is graph processing tooling as well, not only machine learning. Right. So there are people who think that Spark is going to take over, and eventually everybody is going to be doing Spark. Right now, it doesn't sound super plausible because it's so exciting to do so much with one single machine, and most public data sets are not worth putting on a cluster. So it's actually not that easy to find a data set that you really need a cluster to run your models on, right? But this may be changing very fast. Right, so one other interesting feature of this Scala Spark world is that everything is under one roof, right? So you have the Spark core, and then you have all these things, and they are all the same library. So in Python, if you want machine learning, you have Scikit-learn, you have graphs, you have data maybe, or other things. If you want streaming, well, I actually don't know, probably you use a Spark. And SQL engines, well, you have SQL Alchemy and things like that. So they are different libraries and they're not integrated. And this thing being one single core, it's useful because you can go from graphs to data frames, and it's the same thing. And the people who are maintaining the project are building the same thing. So it's not like, oh, let's see if the SQL Alchemy guys are talking to some other group, to the Pandas guys, maybe not. So, right. And apparently, people who are using Spark in production are very happy, and one of the things they report to be happy about is this integration. So they use more than one of these blocks. Right, so the model for Spark is, of course, distributed computing. So how do they do it? They have one driver that sends code running your algorithm to different workers. So the data stays in the workers and the code moves around. So that was Hadoop's main innovation, sort of. So they built on top of that. So the obvious example, word count, you may be sick of seeing word count examples by now. So one thing that is important is that data is immutable. In the Python world, well, tuples are immutable, but it's not that important to operate with data structures that are immutable. In the functional programming world, people are really invested in immutable data types. And by default, everything is immutable in Spark. So that buys you some performance and some characteristics that you're going to appreciate when you're debugging it. Right, so in the map reduce world, this will be a map where you go from this to individual words, and then this will be another map where you assign an integer, which is a count, and then there is one reduce operation where data is shuffled. So you have to move things around machines, and this is costly. You want to avoid that, right? So this situation is still in Spark. There's nothing that has been improved over Hadoop. Okay, now we are going to get into the interesting part if you are using PySpark. So when you run, this is the code for this same word count example. When you run Lambda, this is going to be pipelined into a Python executor, and the entire thing is only executed when you run an action. Like saving and so on. So everything is lazy and waiting for you to. So the default in Spark is not to do any competition. So let's hope we don't have to do anything. And then when somebody actually says that, well, actually bring me data, then you run the entire pipeline. But everything is lazy by default. So these ideas of being lazy and being immutable are strong points. This comes from functional programming languages, nothing new under the sun. But doing it in a distributed way and in an easy way, it's the new thing that Spark brings, right? And it also brings fault tolerance in a totally different way compared to Hadoop. Hadoop was just replicating things like factor of 2 or 3. In Spark, they run the graph of operations. So if you lose a node and some data that should be there is not, then you go back in the graph and recompute everything to create the data. So it's fault tolerant, even though you don't have the replication that Hadoop has. Right. So PySpark on RDDs. So RDDs are these resilient distributed data sets and so on. This is the one place where I've seen the architecture explained. So when you generate a Spark context, you get this Py4j spawned with a socket, and then this will go to the workers and start different Python executors, right? So the interesting thing is that when you call a lambda function to operate on the RDD, each Spark worker forks a Python worker, and data has to move from the JVM to Python and back, just because of the lambda. And this is why performance is not great. And this is why if something dies, the executor really cannot tell. And this is a little bit of a problem. Now, there is a solution for that. So remember that I mentioned that there are some dangers. So this is one danger, right? So there is some overhead forking and serializing things. There is overhead wrapping objects from one language to the other. But also the cluster manager doesn't know anything about Python memory requirements. And that's problematic, because it's very often the case that Spark chokes on one single node having a data structure that doesn't fit the memory of the node. The typical example is a group by operation. So you have, imagine the Facebook graph, and you want to group by number of friends, and you have girls and boys, and then one node has like several million things to count, and then chokes and dies. Another side effect of this wrapping from one language to another is that the error messages are not great. Sometimes you get a stack trace in Python. Sometimes you have to go down to the JVM, and then good luck to you finding what maps to what and so on. Excuse me. Right, so what is the solution to performance problems? The solution is to never do the RDD filtering with lambdas directly, but using data frames. So everybody loves data frames, I imagine. Very useful concept. So you have data frames in Spark. And if you do it like this, it does everything in the JVM, and there is no spamming of another process for Python and so on. If you want UDFs, like functions that you create and so on, and maps and so on, you still need to serialize. But, well, you can do a lot with this syntax without having to resort to go out and create functions. And you can actually write the functions in Scala and then map them if you really want to go that low level. Right, so you may be thinking, well, but why do I want a distributed data frame, which is one of the nice things of using Spark? Well, there is some kind of range where you are perfectly fine with a single node data frame. And I guess it goes up to gigabytes. So nowadays you can buy a machine with multiple gigs and run it as a server and so on. But there is definitely an upper range where you cannot do that. Now the question is whether you want to do this. If you are only interested in machine learning, do you want to run a model on a petabyte of data? Will you sample? If you sample, is the performance about the same? Is the sample good? So all these things are questions that data scientists and more so statisticians are trying to solve right now. So statisticians are sort of scrambling to produce machinery that works with problems like this, where you don't have to do statistical inferences from a sample to a population and so on, but you just use all the data. So yeah, there are criticisms about, well, why do I want to run a model on a petabyte of data, right? But if you wanted to, you can. Right. So the interesting thing is that the way things are going, being on Python is actually pretty convenient, because you're accessing data frames the same way that any other language will access data frames. They all translate everything to a logical plan, and then there's this thing called Daxton that produces an execution model. So performance is about as good. So this is a pretty old graph, so this is about 1 year old. This was RDD in Scala, this was RDD in Python doing these things. It was definitely slower in Python, right? But after data frames were introduced, look at this, all languages are about the same. So that's one reason to say, well, I'm perfectly fine with PySpark, don't have to move, right? Okay, so in machine learning, there are a lot of steps that you have to do normally. And one cool thing about Spark is that you can do it all in one single machine. So you don't have to do ETL on this monster cluster that somebody gave me, and then downsample that somewhere, and then run my models, and then put them back in production in some other machine. So everything can be one single platform, Spark. Right. So everybody likes Scikit-learn. It's a very nice library. It has a lot of things under one single library, which is very impressive. It's very easy to use. It's very easy to create new models and follow the API that they offer and so on. It's pretty up to date, but it normally sticks to one machine, and that's a problem. So you can parallelize things like research on all the cores on that one machine, but that's as far as it gets you, right? Although, having said that, you can try this Scikit-learn package that apparently takes Scikit-learn code and puts it into Spark somehow. I haven't looked at the guts of how this happens, so I'm not going to talk about this. Okay, what if you had to do machine learning with Hadoop? So basically, you are screwed, because it's so fantastically inefficient. So it touches the hard drive for everything, and that's just not a very good idea, because most machine learning algorithms are iterative, like think about gradient descent and so on. Every time you do an iteration, you touch disk. So, well, it totally sucks. So it's just what happened is that Spark killed the MapReduce paradigm, and everybody who was running serious jobs in MapReduce has moved to Spark pretty much, at least the banks and so on. So, well, it's easier, it's more efficient in terms of hardware as well, because it's faster. So things that took a week before, you can run them in a day with the same cluster. It uses more memory, but, well, memory is cheap nowadays. And it gives you a whole bunch of new things like streams, machine learning libraries, graphs that you didn't have before. So it's a total win. And in terms of popularity, it's going through the roof and so on, but you know that. Right. Oh, of course, there's reasons to use MapReduce still for things that are like single pass, like ETL jobs and so on. I imagine there is plenty of Hadoop code in production doing that. And if you are not in a hurry, and you have a big cluster, there's no reason to port that. Right, so the interesting thing is that the people who built Spark understood machine learners, which is a huge thing, because Hadoop engineers didn't, basically. And this shows. So they really think about the use case where you have to do things iteratively, and then you keep things in memory. You only split to disk if there is no other option. So it feels very convenient. It feels that somebody understood you. Right, so you have plenty of algorithms that are already implemented, and the ones that are not implemented are sort of coming. But the thing is, it's moving so damn fast that it's actually a problem for people who want to contribute to it, because you may submit a patch and then wait for somebody to integrate it, and in the meantime, a new version has been out, and then you're screwed. Nobody can merge that now. Right, so it's not just one machine learning library. It started with MLlib. It moved to Spark.ml, which is now the de facto standard. So it used to be that Spark.ml was wrapping MLlib solutions, and now it's the other way around. The main difference between these two is that MLlib uses RDDs, which you've seen are not ideal for Python. But Spark.ml uses data frames. And that's totally cool for Python because it's as fast as any other language. System.ml. System.ml is something that IBM came up with. Apparently, it's very interesting. I haven't looked at it much. And this Keystone.ml, it's another library by the MP Lab, the same guys that did Spark. It's kind of early days, alpha or very early beta. They apparently have very good implementations of NLP stuff. So it's something to consider. So don't think for a second that you have to stick to MLlib. So MLlib is definitely the past. Spark.ml is where things are going. And these things are probably worth a look. Maybe the thing that you really need to do is very well implemented here, and then you can just go to that directly. Right. So there are all these things that, if you're familiar with Scikit-learn, are totally familiar to you as well, right? Pipelines, cross-validators, I mean, it's called different, but you have these things, right? The interesting thing is that they have a very elegant design. So a model and a pipeline are the same thing. It's not like in Scikit-learn that a pipeline is one thing and a model is one thing. So they had the advantage of looking at the architecture of things that have been in the market for longer, and then just improve over that. And my guess is that the Scala guys are super deep into computer science, geeky stuff, and they do everything the most efficient way and the most complicated way too. So it's a damn complex language. So if you think that you can pick it up on your commute, which I thought, you're going to be mistaken probably. So it's a very big language. It has many features. It has everything worth mentioning in the history of computer science ended up there somehow. Right. So then what are the advantages of doing everything in Spark, assuming that you want to do everything in Spark? For once, you get hyperparameter tuning on a cluster. So imagine that you've been doing pretty serious exploration of parameters, and you had one single super powerful machine, but it took a few days to test all the combinations of parameters. What if you could just plug that same model and run it under a day? That would be very pleasant. So you can iterate more, you can test more things. You get that for free. So you go to Amazon, you say, okay, give me this number of machines. It's not that expensive. I think I have a cluster running right now that costs me something like 10 euro per day, and it's a pretty serious cluster. There is no real reason to not do it. And I should actually disconnect the cluster. But okay, so this you may have heard before. Data science is 80% dealing with data cleaning, and the 20% remaining is about pitching. So if you have to go and do serious ETL, then why not do it in parallel if it comes for free? So you may be waiting for your data to be cleaned. This is pretty common in Hadoop clusters and so on. Well, just make it faster by moving to Spark. And last thing, but not least important, models that you can run can be a lot bigger. So if you want a model that has 1 billion features, why not? I think one aspect that I don't think people have connected this, the big data guys are not so big into machine learning. And the machine learning guys are not so big into big data. So when you have really complicated models, you barely have enough data to get along with this type of model. But the guys who do super monster data sets, they don't run complex models. They actually run kind of shitty models that can be parallelized easily. So why? So why would you not run a monster deep learning model with thousands of free parameters if you have the data? So this is the interesting part about doing things in parallel, when it's actually not that much overhead. Just you can try more complex models. Right, so hardest problem to scale up in data science, add people, right? So what I've seen is that things in this world are normally very elegant, and bringing people up to speed and adding contributions is kind of easy. Although, this is a problem. People don't publish components. They go for kind of monolithic things or nothing. And this is not ideal. So one example was a pull request implementing nonlinear SVMs that never got merged, and now it's been like 1 year, and now nobody can merge it basically. So that's a pity, because you only have linear SVMs in Spark, which kind of suck. And somebody actually worried and tried to implement, I think it was RBF, and they are there sitting, collecting dust. Right. So you may have heard about datasets, which are a new data type that has the same API as data frames, but it has types. And this is kind of a big deal for Scala people, because they really like their types. So I was in the room when they announced data frames that were untyped, and there was like half the room Python guys doing yay, the other half of the room Scala guys were like, oh, not type safe. So now they have an object that has types, so it's type safe, and it has the nice features of data frame. But this monster thing can actually do error analysis at compile time, which is pretty cool. Right, so I'm going to drive you in the last stretch through 3 projects that I ran both in Python and in scala-Spark, and tell you what I found. So one of them was this Kaggle where you had to predict whether some researchers are going to get a grant. This is an example of a horrible data set that is extremely dirty, lots of missing data, all kind of data transformation. So you test kind of the feature engineering part of the library. Another one, this is actually in progress, is this visual QA competition that is going on right now, where you are given a picture and a question, and you have to answer the question. And surprisingly, the features that do most of the work are mostly an NLP. So this is mostly an NLP task. So you have the vectors for all the features in the image, but most of the work is done by this. So then the last project was some kind of recommender to tell you who to follow on Twitter. So if you want some influencer to know that you're alive, basically, something like what Buffer does, but better, basically using a personalized PageRank to find the influencers and then computing shortest path and then optimizing that path so this guy actually sees you. Buffer only looks at the times that people are awake posting, and that's the only thing that it optimizes. So this is a graph problem, mostly very iterative, personalized PageRank, and so on. So I'm going to tell you my experience building these things in Python R and scala-Spark. So categorical features, we are very used to factors, but they are a little bit of a pain in Scala. You have to do this all kind of handling manually of one-hot encodings and so on. And when you pass things to a model, they have to be in a format that is very unfriendly. You have to call this vector assembler, and it gives you features as a vector of features, not a pandas object or anything human-friendly. It's just a vector of features. Right. The pipelines story, though, is super good. So if you know pipelines Scikit-learn, you know pipelines in Spark. They have the same features. The way they pass parameters are a little bit different. They are a bit more object-oriented. So in Scikit-learn pipelines, you do it with naming conventions, like name of the model, underscore, name of the variable. Here they have this abstraction, of course, but it works very much the same. And you can write custom stages and so on. Okay, the story with NLP, also pretty good. They have all these transformers, and these are the equivalent things on Scikit-learn. So maybe a more proper comparison would be Spacey. It has more NLP stuff. On this side, on the Spark side, they have even implementations of things like embeddings, like word2vec and so on. So totally fine. Now graph stuff. GraphX, to start with, which is the graph library inside the Spark, is not doing great with Python. They don't have a Python API. There is a data structure called graph frames, and that one actually does have bindings for Python, but I tried it and it kind of sucked, so I don't recommend it. Oh, that's my note that I have to finish. So things I didn't like. Well, first things that we liked. The architecture is very modular, very nice. Types all over the place. Model fitting returns a transformer, which is nice. The story about passing parameters is very homogeneous. And you can do ETL and model fitting on the same platform, right? The grid search works really well on multiple machines. So you are like, oh, this is finished already? How come? So you're surprised by how fast it is. Disappointments, feature indexing, it's a pain, this assembly thing. Maximum depth of truth is 30 for whatever reason. You don't have matplotlib or anything nice to plot, really. People use D3. There are some things missing, like nonlinear SVMs, and deep learning is not there native, but there is this library called Deep Learning 4J that plugs in on top of the entire ecosystem. Right, cool things that are coming that you may be interested in. Everything is moving with Spark 2.0 to data frames, which is very good for Python. Persistence, you can save and load pipelines. And this is, I love this idea. So they're unifying the APIs for streams and static datasets with something they call an infinite dataset. So we are used to something that is a rectangular matrix or whatever that is limited, right? What if it was not limited? What if it was, the bottom will be always growing? That's a stream for you, right? A stream is just an infinite dataset. You don't know where it ends. So they have an API that works on both. And this is coming in Spark 2.0, which is pretty cool. Right, so what have Scala and Spark given us? Well, other than distributed datasets, distributed machine learning, being easier and cheaper to run than Hadoop, doing streams, and being easier to deploy, well, what have they given us? So, right, so, okay, I said the superpower for this talk should be you can say yes or maybe to somebody approaching you today to do a project with Scala in Spark, right? That is pretty ambitious. So the way I want to help you say yes is to give you access to a bunch of videos that we made for TypeSafe. No, not TypeSafe, Lightband. Nowadays you have to pay beers if you say TypeSafe in front of them. Anyway, so there are 25 videos where you, like, this is designed for an advanced or intermediate person who knows machine learning already. If you just want to know the how of how to implement things, everything like feature engineering, dealing with missing data and so on a Spark in Scala, just go to this URL and all the videos are there. So that's it. Thank you very much for your attention. Yeah.
So you mentioned a couple of times that that there are no kernel SVMs. You mentioned that it's sad that there are no kernel SVMs in Spark, but there's a good reason for that, right? I mean, if the kernel grows quadratically, so
yeah.
you just want clear approximation.
Yeah.
You can just, like in Scikit-learn nowadays, just use the random kitchen sinks approximation and dump that into a linear calculator, right?
Right, so I'm going to repeat the question for everybody. So one reason why there are no nonlinear kernels in Spark is kind of the obvious thing that it's just very hard to do nonlinear kernels on a cluster, basically. So it may be that it's never going to happen. So people are doing PhDs on this and writing papers, and eventually somebody may come up with an approximation. So I don't think it's hopeless, but yeah. Oh, okay, so you say you can just do the approximation yourself, right? So you don't need anybody to do it for you. Right, yeah. Sure.
Okay, that's all the time we have for questions. If you want to talk to Jose, you can do that offline. He's going to be here for the rest of the day, I promise.
Yeah. Okay.